Hello friends, I am Dr. Shilpa Gupta, Associate Professor, Electrical and Electronics Department, Maharaja Agarsen University, Baddi. Today we are going to discuss about sequential circuits. Basically, in digital electronic circuit design, we have two kinds of circuits, that is combinational circuit and sequential circuit. In combinational circuit, whatever input you are giving to the input terminals, it will produce the output on the basis of the input provided to the input terminal. But in sequential circuits, whenever you provide an input, it will be the output would be generated after assessing the input. Plus, if you are giving any clock signal or timing signal to the circuit, and the output that was previously generated out of that circuit, that is sequential circuit. So that means sequential circuit are associated with some memory element in which they store the previous outputs generated by the circuit. So these are the sequential circuits. So sequential circuits are can be differentiated by combinational circuits on 2 points, that they contain some kind of timing signals, or maybe called as a clock signal, and they possess some memory in which they store the previous outputs. So let us begin with the presentation. Sequential circuits require memory to store intermediate data or previous outputs. Sequential circuits use periodic signal to determine when to store the values. That means a clock signal is required whenever they need to produce some output, or whenever they want to assess previous outputs. These clock signals are periodic. That means on time and off time of these signals are same. Single bit storage element is called as flip-flop. Flip-flop, one single flip-flop can store one single. The basic type of flip-flop is a latch, and out of that latch, we can make 4 kind of flip-flops, that is SR flip-flop, D flip-flop, JK flip-flop, and T flip-flop. We'll be discussing these in detail in next few slides. Latches are made up from logic gates. These logic gates may contain 3 basic gates, that is AND, or NOT or inverter gate, and 2 universal gates, and NAND and NO. If you are using basic gates, you need to use all 3 of basic gates, that is AND or NOT gate. And if you are using universal gate, you may implement any kind of sequential circuit using single universal gate, that is either NAND gate or NOT gate. Right? This is the block diagram of a sequential circuit. Here is the combinational circuit which is provided with the input. That means in sequential circuit, you need to employ some combinations of gates on which you are putting into inputs. Then those combinational circuits will provide you output, but before providing that output, there is the previous output which are to be feed back to the input terminal through the flip-flop, because as we have already discussed that previous output would be stored in the flip-flop or latches, right? These flip-flop will feed back that previous output to the combinational circuit, and that combinational circuit would assess and will generate the output accordingly on the basis of the present input and the previous or past output. So that is how the output is produced in the sequential circuit. These flip-flop are given with some kind of clock signal or the timing signal, which we have already discussed, that the flip-flops need to have some timing signals so as to make them make them function at the same time, because you need to employ more than one flip-flop in a single circuit. Now, first kind of flip-flop is SR latch. SR latch can be made up of any kind of universal gate. Here, NOR gate has been used for SR latch. Here, 1 is representing 0 input, and zeros are representing 1 inputs. That means we are using inverse logic for NOR gates. Right? Now we have 2 input, S and R. S means set input and R means reset input. Now if we put S and R as 1, 1, we are using inverse logics. So please be careful about it. When I am saying it is 1, it means it is 0 in actual or a normal case, right? If S and R both are 1, 1, they will provide the output which is unchanged. That means if flip-flop is storing the previous output which the flip-flop has been generating was, let us say, 0, then the current output which has to be generated after putting S and R both at 1, 1 would be 0. That means the state of this latch will remain unchanged. Now, if we put 1 to S and 0 to R, it will produce set output. That is, it was 1 at S, so produce 0 output for set. Because as I've already told you that if I'm putting 1 at set, that means I have to reset the signal. Inverse logic we are using here. So 0 means set and 1 means reset. If I'm putting 1 at S, then this flip-flop will produce 0 at set in output. And the latch would be called as a set latch. Now, if I am putting 0 at S and 1 at R, that means I am setting that latch. That means I want to store 1 into this latch. How would it be stored? It would set as 0 at current. Sorry, it would set 1 at current output state. This Q bar is 1 in this case. Now, if S and R both are 0, 0, that means this latch will keep on raising off when would this the both outputs Q and Q bar will try to achieve a state of 0. That means but we have Q and Q bar first output and the second is the complement of the first output. That should not be possible if both output would attain 0, 0, because one should be the complement of the other. So in that case, the condition will become unstable, and this case is not being used in SR flip-flops. Right? This is the NOR gate design. If we go for AND gate design, NAND gate design, it would be normal. If we are putting 0 at any input, that means we are resetting that input. And if we are putting 1 on that input, that means we are setting that. Now for NAND gate design, we again have same table which we have already discussed. In this table, if we put S is equal to 0, R is equal to 0, the system is basically to store the previous output only. No change would be there in the previous output. Whatever was stored in the previous case would retain as it is. Now, if we put S is equal to 0 and R is equal to 1, this flip-flop will be reset because R is 1, reset signal is 1. And if we put S is equal to 1, R is equal to 0, that means we are setting this latch of the flip-flop, that then 1 would be stored in this flip-flop. If we are putting S is equal to 1 and R is equal to 1, that means it is invalid state for this particular latch, because there would be a race in the output who would achieve 1 beforehand, and that would make an unstable state at the output. Okay. Now, as we have already discussed, if we need to make a latch as a flip-flop, then we have to add the clock signal to this flip-flop, and this clock signal basically provides the timing for this particular latch. Timing signals are the clock signals. So if we want to put a clock signal to this, we have to install a set of more gates in the front of the input so as to get the output. So we have put two, because this is a NAND gate design, we have put 2 NAND gate in beforehand, and one input to each NAND gate is S or R accordingly, and the second input to these 2 NAND gate is commonly clock signal. So when this clock is 1, then only this particular flip-flop will work, otherwise it will not work. If now for this clock is 1, then it will this flip-flop will check whether the inputs are 0, 0, 0, 1, 1, 0 and 1, 1. The both these conditions would be verified from here. If both S and R are 0, 0, no change would be there. If S and R 0, 1, it would be reset. If S and R 1, 0, then set state would be there for this flip-flop, and if S and R 1, 1, then invalid state would occur for the clock signal to be 1. And if clock signal is 0, then there is no effect of input to this flip-flop. It will produce no change at the output. So this is the design for NOR gate. This is the design for SR latch using NOR gate with the clock signal, same as was in case of NAND. This is same, and the truth table is also same. Here I've put some bookmark slide marks here. The latch will operate whenever this C signal is set at 0, because you can see here a dash is representing the active low signal. If 0 is there on the signal, that means it is active. If it is 1 on this input signal, then it is inactive in that case. Okay, rest all things are same as was in NOR gate. Now this is the D latch. Now we can make SR flip-flop as D latch also. If we put S and R inputs and we put an inverter between these two inputs, shorted input, we put an inverter between these two, then it become a D flip-flop. D flip-flop is basically a data flip-flop. Whatever applied to the D input is provided at the output. Nothing else is done by the D flip-flop. Here, I will show you the diagram. D flip-flop is D input is connected to S, and there is an inverter between this D and R terminal of the SR flip-flop, and that makes a D flip-flop. Now, you can see from here, if S is 1, or you can say X is, if X is representing, if X is representing, if X is representing S and Y is representing R, then S is directly connected to D and Y is directly connected, Y is connected to complement of D, or there is an inverter gate between D and Y. Then we are using these only two states because there is an inverter gate. If X is 0, Y should always be 1, and if X is 1, then Y should always be 0. So only these two cases we are using for it, and for it clock should be 1 because we have already discussed if it is active high clock, clock should be 1 to for this flip-flop to work, and if it is active low, then clock should be 0 for the flip-flop to work properly, right? In that case, we are considering that clock signal is 1, and these two combinations 0, 1 or 1, 0 we are using for X and Y. Here we have represented this because X is directly connected to D. So if X is 0, D is 0, and if X is 1, D is 1. Clock, we are assuming it is 1, and then it will produce the output. Whatever is on D will be at the Q output, right? If D is equal to 0, Q would be 0, and if D is equal to 1, Q would be 1. That is the case for data flip. Now this is the block diagram of D flip-flop. Here D input is applied. Whatever you are applying at the D input, this X's don't care. Either it is 0 or 1, whatever you are applying to the D input. And then is enable signal, which is directly fed to the clock signal. Enable is to make this particular flip-flop active. Obviously, we are using the active signal as clock signal only. So we will attach this enable signal to the clock only. And this Q is representing the output. Whatever output is applied is produced by this D latch. So this is the block diagram. Now, SR can be represented by these three blocks, these two blocks, and D is representing like this. Two inputs to the SR, S and R, with one output Q, and another is complemented of the Q. And if we are using NOR gate design, then we have to show it like this. Because we are taking active low signals for NOR gate design. So we have put bubble here at the input also, and output is representing first is Q and second is Q bar. Third is D flip-flop. D flip-flop is basically what we have discussed in previous slide is same as here. There is a clock or the timing signal and D input, and one output Q, and another is the complemented form of Q. So it is Shilpa. So latches are based on the combinational gate, as we have already seen that they are dependent upon either NAND gate or NOR gate, and we can make it through basic gates as well. But generally we make it through NAND gate or NOR gate. So we have discussed only two designs. Latch store data even after data input has been removed through it until and unless we provide another clock or another input. The data doesn't remove from those latches. As our latch operate like cross-coupled inverters which control inputs, that is S and R. S is called as set input and R is called as preset input. With additional gates, an SR latch can be converted to D latch. Obviously, we have put an inverter between S and R, and that becomes a D latch. D is simple to understand conceptually because whatever is applied to the D input is produced by the output only. Nothing has to be applied on the input so as to produce the. Okay. So this is all about the summary of latches. Now the flip-flops. Basically, flip-flops are the latch with the timing signals because we have already applied the clock signal to the latches only. So these are only the flip-flops where clock signals are applied. Clock is basically a 2 and 4th motion between 0 and 1 with the same timings. For 0, it would for 0 the same time would be there as was in the 1. So it is just this signal. Now, clock can be considered through three parameters are considered for the clock signals. First is rising edge. This is the rising edge when the clock is going from low to high. And second is trailing edge when the clock signal is going from 1 to 0. That is called trailing edge. And third one is level. Level is when the clock signal is either high or low, or we can say that if clock signal is either throughout 0 or 1. So this is level. Now this is the latch, master slave D flip-flop. In that, one is acting as a master latch and second is acting as a slave latch. Whatever is produced by the master will be produced by the slave. Whatever is footprints are made by the master flip-flop, that footprints will be followed by the slave flip-flop only. But here the difference is, here first master is getting the positive clock, but the slave is getting the negative clock. So we are using the whole time period of a clock from 0 to 0 only. And that means first master will produce the output that will be assessed by the slave, but the slave will not produce output immediately because it is active low. When the clock is 0 only, it will work and produce the output. So you will get the final output at a 1 clock time period. Right. Now, this is the positive edge triggered because flip-flop. You can draw the block diagram of positive edge triggered flip-flop like this. And next is negative edge triggered flip-flop. We'll discuss further in next slides. This is the D input. This is the clock signal, same timing clock signal. Whenever there is high, it would be high at the same time for all the clocks. This particular flip-flop is edge-triggered flip-flop, and that too at a positive edge triggered. Here you can see that it is the clock we are giving to this particular flip-flop is positive edge triggered. So whenever there is a positive edge, it will be triggered and will produce the output accordingly. So here it is the positive edge of the clock. It will assess the input. Input is 0, so output would be 0. At this part, the previous output was 1. Now it will become 0 because of this 0. Now second edge is coming here. The output is 1 at that time. The output will become 1 immediately. Next edge is coming at this point. Here the input is 0. So output becomes 0 immediately. Next positive edge is here. The output is 1. Immediately at this edge, output becomes 1. At this edge, output is 1. Already it was 1, so no change would be there. At this edge, output is 0. Immediately at this edge, the output is going to 0. And that is how the flip-flop will operate. This is the block diagram of positive edge triggered JK flip-flop using D flip-flop. This is the D flip-flop. These are the combinational gates which are used to make it JK flip-flop. Basically, JK flip-flop, in D flip-flop, there was a condition when D flip-flop, SR flip-flop is 1-1, that is invalid. To make that state valid, we have made a flip-flop that is known as JK flip-flop. For 1-1 condition, basically JK flip-flop will toggle. Otherwise, for rest all 3 cases, it will behave as SR flip-flop only. So for that amendment, what we have done, we have fed back the output, cross-coupled output to the input on, and these inputs will now provide some kind of output here after the combination, and that will fed to the D flip-flop and would produce a required output according to this truth table. When J and K both are 0, 0, these AND gate will provide what? This provides 0 because AND gate will provide 0 if any of the input is 0 to the AND gate, right? So this gate would provide 0, and because K is equal to 0, so K bar here, because inverter gate is applied, K bar would be 1. So this AND gate will provide this particular input, and this is Q. So here you will get Q. This 0 plus Q provide Q, and if it is Q at D input, then it will provide Q only, because we know that D flip-flop will provide will be connected to the output directly. That means whatever is the input at this terminal would be provided at the output. If we are providing Q here, it will be provided, it will be directly linked to this output, and Q will be provided. And here we have already mentioned that if J and K both are 0, 0, no change would be there. So no change is there. Now let us take another case. If J is 0 and K is 1. J is 0, again this AND gate will produce 0 output, and K is 1. This AND gate will also produce 0 output. So both 0 plus 0 is 0, and whatever is at D will be at output. So output would be 0. Now another case, when J is 1 and K is 0. J is 1 means this will provide Q bar because it is connected to Q bar from here. So here it is Q bar, the output here it is Q bar. And if it is K is 0 in this case, it would be 1. The output here, it is second output, that is Q. So it is Q bar and it is Q. And we know that Q bar plus Q is, according to the binary theorem, any input with its complement added will give you 1 always. So here we will get 1, and whatever is at the D input will be at the output. So in this case, we'll get 1 output. So here we have shown already that 1 output would be there. Now let us take another example that J and K both are 1, 1. J is 1, K is 1. When J is 1, you will get Q bar here. And when K is 1, here you will get 0. So output of this AND gate is 0. So here Q bar and here 0. Q bar plus 0 is Q bar. You will get Q bar here. Whatever is the input here will be provided at the output. So Q will be toggled and the output would be Q bar. Okay. So that is how, if Q bar, here it is Q bar, then it will fed back to this particular gate Q bar, and here you will get Q. So this will fed back, this Q will be fed back to the J input, and for the next case, it is Q. Q plus 0 would provide you Q. For the next clock cycle, it will again toggle from Q bar to Q. It will become Q. So that is how it will toggle every time whenever it detects the clock signal or the positive edge triggered clock signal, right? So that is how we have made unstable state of SR flip-flop. We have converted that state into a stable state, which is toggling state. Now another fourth flip-flop is T flip-flop or a toggle flip-flop. That toggle flip-flop will be made from JK flip-flop by connecting these two signals, shorting these two signals J and K. That will become our toggle flip-flop by directly connecting J to T. T is the input of toggle flip-flop, and shorting these J and K, that will make a toggle. These are the timing diagrams. Here it is toggle flip-flop. We just have shorted J and K, and we directly connect J input to the T input, and that becomes a toggle flip-flop. We are using this particular combination here. This is when J R K both are 1, 1, and when J R K both are 0, 0. When J and K both are 0, 0, that means T is equal to 0. That means no change would be there. And when both are J and K are 1, 1, that is T is equal to 1, then toggling case would be there. That is only used in toggle flip-flop. That this is the toggle flip-flop. When it is 0, no change would be there. When it is 1, toggling would be there. So this is all about the flip-flops and the latches. These flip-flops, what we have discussed, are the synchronous flip-flops, but we can make it asynchronous flip-flops when we connect flip-flops, cascaded flip-flop with different clocks. That becomes a asynchronous design. And when we make a cascaded flip-flop and fed them with the same timing signal, it would become a synchronous. So this is the flip-flop, and that is how we can connect the flip-flop in cascade form with the same clock. This is the synchronous design of flip-flops. Now, flip-flops are the powerful storage element, where D flip-flop is the simplest and most widely used. Asynchronous input allow for clearing and presetting the flip-flop outputs. Multiple flip-flops allow for data storage and combined storage and logic to make a computational circuit. So this is all about the flip-flops.